And we're now recording. All right, so we're up to 5.3, doing something called the fundamental theorem of calculus. 2 days for that. Okay, Friday, I'm going to give you the majority of the time for the quiz. It's one of those quizzes where, okay, I'm not sure I would ask you the whole question on an exam, but for a quiz, I'm willing to do that. Okay, so Friday, expect very little lecture. I haven't decided, maybe I'll do no lecture. Maybe it depends on how far I get today and tomorrow. Okay, I'm going to have you do one of these Riemann sums, and I'll more than likely have you do all three: left endpoints, right endpoints, and midpoints. So I'll give you a function, ask you to compute the sum using the left endpoints, find the sum using the right endpoints, and also the midpoints. Okay, now on an exam, I'm probably not going to ask you all three. I might just ask you to do the midpoints or just the left endpoints or something like that. Okay, but for the quiz, I'll give you, the majority of the class period to work on it. I want you to be able to show me that you can do all of them. Okay, and if that's all we do that day, I'm still okay. We have all this. If I don't finish everything by here, I've got buffer days ahead here. Okay, so again, let's go ahead and set Thursday the 20th as the last exam. If I finish early, I'll just go ahead and start reviewing for the final. But Wednesday the 19th is our usual question and answer day, if you want to ask any questions pertaining to the test. Okay, and then Friday again, we'll review for the final. Now, I'm not guaranteeing I can give you back your test by Friday the 21st. I'll get it to you over the weekend like normal. Okay, I should have a solution key out for you so you can study off the solution key. Okay, so you'll have that ready to prepare for the final, which is Monday the 24th. Okay, as far as cheat sheets concerned, you can just bring in all the previous cheat sheets. So let's officially say you can have 5 cheat sheets for the final, because you're allowed 1 formula sheet for each test. So just bring this same cheat sheet for the first test, second test, third test, fourth test, fifth test. You don't have to make up a new one. Hopefully you didn't throw it away. If you threw it away, then I guess you do have to make up a new one. But if you still have that old formula sheet, don't reinvent the wheel. Just keep it and bring it for all of them for the final exam, Monday the 24th. So again, how do I study for the final? Just study off the old exams. And the most likely scenario is I'll take, say, 3 or 4 questions from each exam. Again, not promising you that the very same questions, but questions that are like it. And that'll be how I construct the final exam. Okay. All right, so that's that. Any questions? Let me check the chat. Okay, so some of you just joined. Okay, that's fine. All right, so I'll get you a little bit later. Okay, so let's start 5.3. I introduced a very little of it last time. We have something called an area function, as it were. Okay, on page 392, topic is fundamental theorem of calculus. There's 2 forms of it. So we have sort of an area function. G of x is the integral from a to x of f of t dt. A is constant, x is variable. Okay, that's going to be important when we do that later. And here's the picture. Okay, so figure 1, if I move x to the left or to the right, I get a different area. If I move x on top of a, then the answer is 0. There is no area that's there. Okay, and we talked about this. Okay, so G of 1 is 1. That's the total area. G of 2 is 3, total area. G of 3 is about 4.3. G of 4 is about 3. Remember, everything above the x-axis as an area is counted as positive. Everything below the x-axis is counted as a negative. G of 5 is approximately 1.7. Okay, so we have a couple of problems on the homework that are just like that. So let's address them right now. Okay, so 5.3. And the homework is 2, 3, 7 to 41 odd, 59, 61, 63. So let me show that to you for those of you that aren't getting the book. There's question 2. There's question 3. Then we have 7 through 41. There's that. And page 400. Oh, page 400. Can you imagine that? We've had 400 pages of calculus, right? So, there's all that. Okay, and then let's see. Check, we had to go to 41, so I don't have to show you those. Okay, 59, 61, and 63. And there they are. Okay. So let's go to problem 2. All right, g of x is the integral from 0 to x of f of t dt, where f is the function whose graph is shown. Okay. Evaluate g of x for x equals 0, 1, 2, 3, 4, 5, 6. Estimate g of 7. Where does g have a maximum value, minimum value? Sketch a rough graph of g. Okay, again, this is best done if I project this and then use a whiteboard, but I don't have that possibility. But let's see what we can do. So we're integrating from 0 to x, talking about the true area bounded by the graph and 0 to x. All right, so they want g of x from 0 to 7, actually. So I made a little table here. 0, 1, 2, 3, 4, 5, 6, 7. Okay. All right, g of 0, it's the integral from 0 to 0. How much area is there between 0 and 0? Well, 0. Okay, maybe I can go like this. I can barely show you both, yeah. Okay, plug in 1. G of 1, what's the area bounded by the graph and the x-axis? Half a unit, 0.5. Okay, g of 2, by the time I get to 2, maybe it's better if I use my ruler to cover up the rest of the graph. Okay, so that's positive a half. This is below the x-axis, negative a half, for a grand total of 0. So g of 2 is 0. G of 3, positive a half, negative a half, negative a half. Grand total of negative a half. G of 4, 1, 2, 3, 4. Positive a half, negative a half, negative a half, positive half. Again, we're bounding the graph with the x-axis. So it's this is a positive half. This right here is negative half. There's another negative half. There's a positive half. So net total is 0. Okay, and then G of 5. Okay, so I already know up to here is 0. Positive a half, negative half, negative half, positive. So just between 4 and 5. 4 and 5, I have 1 square and a half a square. So 1.5. And then from 0 to 6, again, I already know from 0 to 4 is 0. So I just need to go 4 to 6. Well, between 5 and 6, I picked up 2.5 more. All right, only look between 5 and 6, 1, 2.5. So add 2.5 to 1.5 and I get 4. Okay, and then B, estimate G of 7. You can see why they say estimate, because it's curved. Okay, so what did I do? If I draw a straight line right here, I would say that's about 1.5, right? Draw a straight line segment from here to here. There's 1, 2, 3. So if I go in a straight line right there, it's 1.5. Because of the curve, it's a little bit more than 1.5. So I guess it was about 2 more. So I add 2 to the function value of 6. So 7, 6. That's what I got. Okay. That's the way it works. Where does G have a maximum value? Where does it have a minimum value? Well, just take a look at the table. Maximum is at 7, 6. Minimum is at 3, negative 0.5. Which means as I play this game and I move along and I pick up integrals, which is positive and negative area, up to 3, that's where I get the greatest amount of net negative area, right? Positive a half, negative half, negative half. And then where do I get the most net positive area? Well, the graph after that is all positive, so it would make sense that it would happen to be at the very end. So maximum at 7, 6, minimum at 3, comma, negative 0.5. Sketch a rough graph of G. Well, I just plot all these points. X versus G of X. So 0, 0, 1, comma, 0.5, 2, comma, 0, 3, comma, negative 0.5, 4, comma, 0, 5, comma, 1.5, 6, comma, 4, and 7, comma, 6. So here's a rough sketch of G. That's all. All right, so let me show you this again for focusing purposes. Okay. And that's the answer to 2. And I'll raise it up again for better focus. And I'll do 3 now. This is better for focusing, but I have to put the book down now. 3 should be better because there are no curves. Everything is a straight line segment. So I can find areas of triangles and rectangles and so forth, right? Okay, same thing. G of X, integral from 0 to X of f of t dt. Evaluate G of 0, 1, 2, blah, blah, blah. Okay, net area under the graph where anything above the x-axis is positive, anything below the x-axis is negative. Well, in this case, I guess it's a t-axis. Okay, it says evaluate G of 0, 1, 2, 3, and 6. I might as well do 4, 5, and 6 also. Okay, so this one I can't quite show you the whole thing unless I curl the paper. So yeah, maybe I'll curl the paper. Go like so. Okay, net area under the graph. 0, 0, right? How much area is there from 0 to 0? 0. Now I move up to 1. What's the net area? 2. Move here. How much additional did I add? 1, 2, and 3. Okay, there's a square, there's a square. This is 1 unit because I see this whole thing is 2 and I chopped it in half. So that's 1, so a net gain of 3. So 2 plus 3 is 5, right? Or if you want to start at the beginning, 1, 2, 3, 4, and 5. Between 2 and 3, just here to here, what did I gain? Well, if I take all of this, that's 1, 2, 3, 4, 4 squares. I cut it in half with that line segment. So I gain 2. So 7. And now at G of 4, 1, 2, 3, 4, I'm down half a unit. So I lose half a unit, 6.5. And then between 4 and 5, it looks like I lose another 1.5. 1.5 units below the t-axis. Okay, that's a whole square, that's a half a square. So I subtract 1.5, so G of 5 is now 5. The net amount above the x-axis is 5. Okay, again, everything above the t-axis or x-axis in general is positive, anything below is negative. Okay, then at 6, more negative, 1, 2 below, so I lose another 2. So G of 6 is 3. And then 7, I have this piece right here. That's a loss of another 1. It's below the x-axis. I know this is 2. That cuts it in half. So I drop another 1. So 7, 2. Okay. So that's where it works. On what interval is G increasing? G is increasing when I pick up more and more positive area. So that's everywhere between 0 and 3. So between 0 and 3 on that interval, G is increasing. Where do we have the maximum value? Right here, because after 3, I start picking up negative values. So the maximum is the 0.3, 7, as you can see from the chart. Right, the maximum value is 3, 7. And the reason why I put this is this notation looks the same. I mean, if you just saw this out of context, this could have two meanings, right? This could be a point, x, y, or it could be an interval, right, between two x values or t values. This is an interval from 0 to 3. This is a point from 3 to 7. All right, and once again, all they say is to sketch a graph. Sketch a rough graph. So I just plot 0, 0, 1, 2. And you can do this as well as I can. 2, 5, 1, 2, 1, 2, 3, 4, 5. 3, 7, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. Then it starts to go down. 4, 6.5. 5, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. 6, 3, 1, 2, 3, 4, 5, 6, 1, 2, 3. 7, 2, 1, 2, 3, 4, 5, 6, 7, 1, 2. And just play connect the dots. That's a rough sketch of the function. Okay. All right, so that's it for that. Okay, let me check the chat if you have any questions. Doesn't look like it. All right, so now we're leading up to something called the fundamental theorem of calculus. And you definitely want to put this on your cheat sheet. There's two parts to the fundamental theorem of calculus. Now, if you want to see both of them at the same time on page 398, they're both here. I'm doing fundamental theorem of calculus part 1 right now. So you see there's a 1 and a 2, right? Part 1, part 2, you may put them both on your cheat sheet. Yet if we were meeting face to face, I'd make you memorize them, but we're not. Okay, so let me develop fundamental theorem of calculus part 1. Okay, so I have to show you the derivation of it. Okay, so fundamental theorem of calculus, part 1. Sometimes we write FTC 1 and FTC 2. Fundamental theorem of calculus, FTC, part 1. All right, suppose I have g of x is the integral from a to x of f of t dt, one of these area functions. Okay, this is constant, this is a variable. So on the bottom, it's a constant, the top is a variable. So a is fixed, but imagine x moving back and forth. Okay, f is a continuous function. Okay, so in order to use the fundamental theorem of calculus, f is continuous. All the functions that we're going to do, they're continuous. You don't really have to worry about that. Okay, I made a little picture here. Here's x. Here's x plus h. And then I put something in green called x star. So where is x star? X star is anything between x and x plus h. Okay, it could be the midpoint. It could be the left endpoint. It could be the right endpoint. It could be the point that's 2/3 of the way across. It could be the point that's 10% of the way across. It actually doesn't matter. Okay, it's just some point between x and x plus h. So x between x less than or equal to x star, less than or equal to x plus h. Now, g of x plus h minus g of x. G of x plus h is this. I'll trace it out. Here, all the way out to here, down and back, right? It's the net area under the graph from a to x plus h. I'll trace it one more time. Up, all the way here, down and back. Now, what is g of x? G of x is the area under the curve from A to x. So up, over, down, back. One more time. Up, like that, down, and back. Okay, so if I subtract these two, I have that red region, right? Okay, I'm taking the bigger area minus a smaller area, and I have this, which is almost a rectangle. As long as f is a continuous function, then I almost have a rectangle. So it's approximately f of x star times h, right? Base times height. Okay, base is h. I went from x to x plus h. That's h. What's the height? Well, I can approximate it with a typical point, if it's the midpoint or left-hand point or right-hand point, or it doesn't matter, f of x star h. Okay, divide both sides by h. G of x plus h minus g of x all over h is approximately f of x star. Then I take the limit as h approaches 0 on both sides. Put limit h approaches 0 here, limit h approaches 0 here. So limit h approaches 0, g of x plus h minus g of x over h equals limit h approaches 0, f of x star. This, you might recall, that's the very definition of a derivative. Okay, way back in chapter 2, the limit definition of derivative g prime of x. Okay, as h approaches 0 in this picture, then it doesn't matter where x star is, it gets squinched closer and closer to x. So this becomes f of x. In other words, g prime of x is f of x. Right. What does this all mean? This leads us to the fundamental theorem of calculus part 1, sometimes called FTC1. Okay, you're not responsible for this derivation. I'm responsible for the derivation, and just to show it to you, what are you responsible for? For being able to use the formula and the theorem. So here's the fundamental theorem of calculus part 1, and this is how to do the homework problems from today. Given a continuous function f, and g of x is defined to be the integral from a to x of f of t dt. So what's the difference between f of t and f of x? Really nothing. But if you have x here, technically you're not supposed to have x here. So we switch to a different letter t. So g of x is one of these area functions, these weird area functions. Integral from a to x, f of t dt. Key thing, this has to be a constant. This has to be a variable. Then g prime of x is equal to f of x. Okay. In some strange sense, if you take a derivative of an antiderivative, you get back where you started, which kind of makes sense. Okay. To do the problems, all you really do to take the derivative is take that variable there and stick it here. So g prime of x is f of x. You're actually not going to differentiate anything. You're not actually anti-differentiating anything. You simply put this thing right here to find a derivative. Okay, so one more time, g of x is the integral from a to x, must be constant here, variable here, f of t dt, then g prime of x is equal to f of x. Okay, so I will show you some of that right now. So if you only want to look at fundamental theorem of calculus part 1, here it is on page 394. F is continuous on a closed interval from a to b. G of x is defined as the integral from a to x of f of t dt. Okay. Then that means g of x is continuous on closed interval a to b, differentiable open interval a to b, and g prime of x equals f of x. Granted, for most of the problems that we're doing, this is always going to be true. They're going to be continuous differentiable. So to take the derivative of this function, think derivative of an integral. So wait a minute, if I take a derivative of an integral, I'm back to where I started from, right? It's kind of like saying square and square root. It's like saying add 5, subtract 5, right? So if I take the derivative of an integral, I just get back to my original function, which really means all I have to do is take that variable x and put it right there. G prime of x is f of x. Okay, and that's exactly what I have here. So f is continuous. It's going to pretty much be continuous for all the problems we do. G of x is the integral from a to x. You must have constant here, variable here, f of t dt. So if it doesn't look like this, well, you have to change it. Okay, then g prime of x is equal to f of x. Okay, so make sure that you have constant here, variable here. Okay, now something else that we need to use is this thing that I mentioned the other day. Page 385. This one. Integral from b to a is the opposite of the integral from a to b. Right? Mention that. Integral from b to a, switch the top and the bottom and put a negative sign in front of the whole thing. The reason for that is because the delta x becomes negative in one of the instances. Okay, and delta x in the limit becomes dx. All right. So how do we do the homework problems, right? So the problems that we're going to work with for fundamental theorem of calculus part 1, FTC 1, we need that for 7 through 13. Well, I guess up to 17. Up to 17. And then also the problems at the end, 59, 61, and 63. And I apologize if it looks like it's disconnected. It's because the author did it that way. In my opinion, 59, 61, and 63 belongs right after problem 17, but the author decided not to do that. Okay, so I'll show you how to do that. So again, right now, the problems that you know that we can do are 7 through 17. It says, use the fundamental theorem of calculus part 1 to find the derivative of the function. So we're going to differentiate the function. We can do everything up to 17. And then the last 3 problems, 59, 61, and 63. We don't know how to do 19 through 43, I guess, or 41 yet, but we will shortly. Okay, so here we go. Okay, 7, g of x, integral from 0 to x of the square root of t plus t cubed dt. All right, does this look like this? Constant on the bottom, variable on the top. 0, x. Yes, it does. So how do I find a derivative? All you do is simply put that x in place of t. So g prime of x, square root of x plus x cubed. That's it, you're done. Okay. You don't actually differentiate this. You don't actually try to take an antiderivative of it. You're integrating here, and then you immediately differentiate. Okay, so don't try to take the derivative of this. Don't go like t plus t cubed to the 1/2 and then chain root 1/2, t plus t cubed to the negative 1/2 times chain root. And don't need to do that. Don't try to integrate that power rule or whatnot. Just simply put that x right there and right there. That's g prime of x. See, that's too easy. You're right. It is too easy. In fact, my expression sometimes is it's so easy it's hard. I mean, you think you have to do something more. It can't be that easy. There's got to be more I got to do, right? But no, there isn't. Just simply plug that right in there. Oh, that's kind of true. It's not quite, they're not all quite that easy, but there's little tricks to it, I guess is the way I should say it. Okay, number 9, g of s, doesn't matter what letter they pick. G of s is the integral from 5 to s of t minus t squared to the 8th power dt. Okay, constant on the bottom, variable on the top. Is that what we want? Constant on the bottom, variable on the top. Yes, it's perfect. So what is g prime of s? Don't actually differentiate anything. Simply put the s in place of t right there, right there. S minus s squared to the 8th power. That's it for that one. Now, mix it up a little bit. 11. Capital F of x is integral from x to 0 of radical 1 plus secant t dt. All right. Constant, variable. What do we have? Variable, constant. So what do? Take a look. We apply that property. Switch them around and put a negative. And then it's the way that I want it. Constant, variable, right? So we're taking advantage of that rule. That the integral from b to a is the opposite of the integral from a to b. Right? Page 385. That one. Integral from b to a is the opposite of the integral from a to b. So put a negative sign in front of the whole thing and then integrate from 0 to x. Now it's perfect. So the rest is the same, except you have to remember to put the minus sign. So now f prime of x is negative square root of, put the x right over there, 1 plus secant x. Right, next complication. What if they don't give me just x or s or whatever, but a function like e to the x or 3x plus 2 or whatever? Okay. So problem 13. Okay. There's an e to the x on the top. 15, 3x plus 2, 17, square root of x, and it's out of order, but you know, same thing. So that's going to be a variety of the chain root. So h of x is one integral from 1 to e to the x ln t dt. So first of all, is it the right orientation, so to speak? I want constant on the bottom, variable on the top. Constant, variable, that's fine. So it was reversed. If e to the x was here and 1 was here, we know what to do now. Switch it around, put a minus sign. Okay, so I have to show you a little bit of background. When you work this problem out, you don't actually have to write all of this stuff. I'll show you a shortcut. But we know what to do if there's a single letter, like u. So I said, okay, what if I just call it u? Let u equal e to the x. That means h of x is basically integral from 1 to u ln t dt. So it's a single letter. So if it's a single letter, it's just like the ones we did, right? Just like problem 7, like problem 9, number 11, even though I just switched these, it was a single letter. So now we know what to do. But ultimately, we're trying to find h prime of x, which means dh dx. H prime of x is dh dx. Okay, well, by the chain root, the Leibniz notation for the chain root is dh du times du dx. Okay, you might recall this is something called the Leibniz notation. The D stuff. Leibniz, again, is one of the co-founders of calculus along with Sir Isaac Newton. So dh dx is dh du times du dx. And see how it kind of looks like the du's can cancel out, right? If I cancel out the du's, then it looks like dh dx. Okay, so what's dh du? If I were differentiating with the u being the variable, I just do what I normally do. Just put a u right here, ln u. Times du dx, that's u prime of x. Okay, now what was u? It was e to the x. So I put ln e to the x times u prime of x. U prime of x is just the derivative. So what's the derivative of e to the x? E to the x. And then we know from algebra, this comes out to be just x, right? X times e to the x Final answer, x e to the x. Okay, so what happened, or what's a nice shortcut? Here's the shortcut. What happened back in the original? You can put that e to the x right there, but then by the chain rule, it's times the derivative of this expression up here. Okay, so you don't have to run through all of this unless you feel like it. Okay, shortcut. If you don't just have x, like the previous problems, just plug in x, plug in s or x. Okay, what if you have e to the x? Start off just like before, and this is kind of the theme of all chain rule problems, right? Put the e to the x right there, ln e to the x, and then times the derivative of e to the x. Okay, so shortcut again. You have a function here. Put the e to the x there, ln e to the x, ln e to the x, which comes out to be x, and then times the derivative of e to the x, which is also e to the x. So I'll let you go straight from here to here. In fact, that's what I prefer you have. I don't want to see all this extra stuff. Okay, so one more time. If you just have x, plug it in. If you have a function of x like e to the x, plug it in, ln e to the x, and then times the derivative of that thing floating up there. Where'd it go? Derivative of e to the x is e to the x. And then ln e to the x is the same as x. So x times e to the x.
Can you leave the answer like that?
Okay, I'm sorry, I didn't quite hear that, or?
I'm sorry, I'll repeat it. Can you leave the answer like that? Like that's the final answer?
You leave the answer like so, yeah. X e to
Okay.
the x, that's what I want you to do.
Thank you.
Okay, you're welcome. Any other questions, please? You can either mute yourself or put it in the chat. Double check, I don't see it there. So this is another variation of the chain rule when you have this derivative and integral stuff. And I'll try to highlight that with the next two examples. Yeah, it's just about, looks like I'm doing all the problems, but that's okay. Okay, 15. So now for the shortcut. Y equals blah, blah, blah. So algorithm, what do I do? Okay, 1, 3x plus 2. First, let's check. Constant on the bottom, variable on the top. Is that true? Constant on the bottom, variable on the top. Correct. So if all they said was x on the top, and by the way, it doesn't matter what number you have here. It can be 1, it can be pi, it can be a billion, negative a million. Okay, it doesn't matter. As long as there's a constant on the bottom, the fundamental theorem of calculus part 1 that we proved, we went through the proof of it, okay, that it'll work regardless of what the number is here. So if all you said here was x, final answer is just put an x there and an x there. Okay, algorithm, it's 3x plus 2. So right here, put parentheses 3x plus 2. Right here, put parentheses 3x plus 2. And then by the chain rule, times the derivative of 3x plus 2. What is the derivative of 3x plus 2? 3. Okay, so here's the way it works. Y prime, and mind you, you're actually taking a derivative. So technically you shouldn't say y, it's y prime. Okay, so 3x plus 2 goes here. 3x plus 2 goes here. So 1 plus parentheses 3x plus 2 cubed times the derivative of 3x plus 2, 3. And you can leave it like that. Don't bother to multiply that out. And if you feel like it, you can go 3 times 3x plus 2 is what, 9x plus 6. You don't have to. The main thing is we're getting the calculus here. Okay, one more like that, but a little harder is 17. And yeah, it kind of looks like I've just about done all the problems of this type, but that's okay, I don't care. 17, y equals the integral from radical x to pi over 4, theta tangent theta d theta. Okay, variable on the bottom, constant on the top. In order to use fundamental theorem of calculus part 1, how does it have to look? Constant, bottom, variable, top. This is reversed. Variable, constant. So we know what to do. switch them around, put a negative. So negative integral pi over 4 on the bottom, radical x on top, theta, tan theta, d theta. And keep in mind, square root of x means x to the 1/2. Right, so algorithm for the derivative. I am doing y prime. Square root of x, where do I put it? Right here and right here. And then don't worry about the d theta. And then times the derivative of radical x. So that comes afterwards. So that's the variation of the chain rule in this case. Right, so here we go. So y prime is put radical x right there, radical x, tangent radical x, times the derivative of radical x, which is like saying the derivative of x to the 1/2, 1/2 x at a negative 1/2. We know what that means. Put the 2 in the bottom, put square root of x on the bottom. So I have radical x, tan radical x over 2 radical x. Looks like the radical x's can cancel out. Final answer, 1/2 tangent of radical x. And there we go. Okay, so that's how you do that problem. Okay, so here's one where we had to switch once again. So two things going on. I had to switch these and I had a chain rule, right? So constant supposed to be in the bottom, variables on the top. So I switch it, put a negative, put radical x right there, put radical x right there, and then times the derivative of radical x. Okay, don't actually try to take the derivative of theta, tan theta. Don't try to integrate theta, tan theta. Just simply put it in here, put it in here. Okay, so that's it for those kind of problems. So 7 through 17, I basically blew through all of them. Okay, what's happening with the rest of the problems, 59, 61, and 63? You look at 59. There's a variable expression on both the top and the bottom. 61, variable top and bottom, variable top and bottom. Okay, they actually give you a hint. Okay, I'll talk quickly about the hint, but I'll show you where it came from, and then I'll be done for the day. So we have to recall this rule. Page 387. The integral from A to C plus the integral from C to B is equal to the integral from A to B. Right? Integral from A to C, the left, the darker blue, plus the integral from C to B, the light blue, equals the integral from A to B, the total all the way from A to B. Okay. So for 59, 61, and 63, which I'll show you tomorrow, they say introduce a constant. They put 0. 0 is as good as anything else. So 59, integral from 2x to 3x, we can say is the integral from 2x to 0 plus the integral from 0 to 3x. You don't have to pick 0. You could pick any number, A in general. So it can be 21 or pi or your favorite number. But if you want to make it easier and stuff, just put 0. Okay, so one more time, integral from 2x to 0 plus the integral from 0 to 3x is equal to the integral from 2x to 3x. And now we know how to do both of these. This is perfect, constant, variable. This is backwards, variable, constant. We know what to do. Switch them around, put a negative. And that'll take care of 59, 61, and 63, but we're out of time for today, so I'll show you that starting tomorrow. Okay, so tomorrow I'll do the rest of these, and then I'll introduce fundamental theorem of calculus part 2. And that will be the game plan for tomorrow. Okay, so that's about it. Does anybody have any questions? Let me check the chat. Yeah, anybody join late, please put your name in the chat now so I can get you a little bit later. Okay, all right, don't see anything else. All right, any other questions, please? Otherwise, that's it for today. All right, I don't see or hear anything, so that'll be it. Okay, have a good day, everybody. See you next time. Okay, bye, everybody.